So just now we found that if this mass moves by a distance of x1, then this pulley will move by a distance of x1 over 2. So now our goal is to find that if this pulley moves, we need to decide how this pulley would then be moved, which would help us decide how this pulley would be moved, which would in turn help us decide how this mass would be moved. And using this, we can determine the relationship between the acceleration of these two masses. So we've completed the first step. We found that for every displacement of x1, so if this mass moves down by a distance of x1, then this pulley would move up by a distance of x1 over 2. So if this moves down by 2 centimeters, then this pulley would move up by 1 centimeter. So now our next step is to find if this pulley moves up by a distance of x2, then we want to find how much this pulley would go up. So in order to reason our way to the movement, the relationship of the movement between these two pulleys, we're going to have to draw a diagram. So now I'm going to focus on this system over here. I'm going to focus on this particular string. So let's draw a diagram. So you can see from the setup, so for this particular string, there is this vertical component, and then it's attached to this pulley, and then there's this curved section, and then it goes up. And this is the point where it attaches itself to the other pulley. So when that other pulley goes up, the resulting configuration will look something like this. So obviously the pulley would be pulled up, and then this tip would be somewhere higher in this position. So now we want to find that, so we know that as this pulley goes up, so let's just get rid of all this stuff. So as this pulley goes up by a distance of x2, this tip over here, so this point over here, would go up by a distance of x2. So that means the difference in distance between these 2 points is equal to x2. So now the next step is to find how much this pulley would go up. So I want to find the distance between these 2 points. So let's just say this is the center of the pulley. And we can see that this pulley would be moved up, but we're not quite sure what the distance would be. So let's just call this distance x3. So our goal now is to find what x3 should be. And then we can do that by considering, once again, the conservation of string. So we know that the total length of string would be the same no matter how you move this system. So let's just use this fact to help us deduce what x3 should be. So I'm going to define some lengths over here. So let's just say this initial length is equal to L. And then let's just say this for this curved section over here. So this curved section over here. So let's just say it has a distance of L1. And then for this section over here, let's just say it has a distance of L2. So first of all, so we've defined the 3 kind of segments of this string over here. So let's try to do the same thing for this diagram. So we know that this part is going to be something slightly less than L, right? And then you can see that the distance, the difference between these two lengths is that this length over here is going to be equal to L minus x3. So if you compare, this straight part ends at the point where it is horizontal with at the same level with the center of the pulley, and then as you can see, the difference between the lengths is exactly equal to x3. So this length is equal to L minus x3. And then we can apply the same reasoning to this length over here. So you can see that this original length is equal to L2, and then if you would draw a line over here, so you know that this is equal to L2, and then we know that this distance is equal to x3. So this smaller distance over here, this is going to be equal to L2 minus x3. So we know that this larger distance over here is going to be the sum of these 2 distances, which is equal to x2 plus L2 minus x3. So there we have it. So now we can use the conservation of string to derive some results. So the total length of string on this side is equal to L, this straight part, plus L1, this curved part, plus L2, this second straight part. And this is equal to the total length of string in this final configuration. So we have L minus x3 plus the curved part, L1, plus this section over here, which we found is equal to x2 plus L2 minus x3. So now obviously you can see that some of these terms, they can be cancelled out. So you can see that it doesn't really matter what these actual lengths are because they just cancel out in the end. So in the end you can see that 2x3 is equal to x2. So this is a very important result. So what this means is that when this pulley goes up by a distance of x2, this pulley would go up as well, but it would go up only by a distance of x2 divided by 2. And because we know that for a distance of x1, x2 is going to be equal to x1 divided by 2, we know that when this goes down by x1, this will go up by x2, and this would go up by x2 over 2, so that means this would go up by x1 over 4. So you can see the relationship between all these distances. So when this goes down, this would go up by half the distance, and this would only go up, this pulley would only go up by 1/4 of the distance. And then you can see that we can apply the exact same reasoning to this pulley over here. So that means this pulley would, when this pulley goes up by a distance of x3, this pulley would go up by a distance of x3 over 2, which is of course equal to x1 over 8. So you can see that the distance by which these pulleys goes up, they're going to keep decreasing by a factor of 1/2. So this goes up by 1/2, this goes up by x1 over 4, this goes up by x1 over 8. And then when this goes up by x1 over 8, that means this mass also goes up by x1 over 8. And this is a very important result. All we really set out to do wasn't really to find how these pulleys would move, but it was really to find the relationship between the movements of these two masses, and we have achieved such a thing. We know that if this mass goes down by x1, so let's just draw this out. So when the rightmost mass, so this one over here, if it goes down by a distance of x1, this other mass over here, the one at the bottom, it would go up by a distance of x1 divided by 8. So we can immediately arrive at a relationship. So let's just say the displacement of this mass is equal to x2. So I know this is kind of confusing because I used x2 before, but this x2 is going to be different from the x2 I used before. So when this, so the displacement of this mass is equal to x2, and then this is equal to negative x1 over 8. So what this means is that the displacement of this mass is equal to the displacement of this mass, and you give it a negative sign to denote that they move in opposite directions, and that the magnitude is going to be adjusted by a factor of 1/8. So if this goes down by 8 centimeters, this is going to go up by 1 centimeter. So this is the result that we're looking for. And then all we have to do now is to take the time derivative of both sides 2 times. So you can see that the a2, the acceleration of this second mass, is equal to negative a1 over 8. So this is the relationship we're after. So using this, now we can combine it with our other 2 equations to come up with our solution. So let's do just that. So we have a2 equal to negative a1 over 8. So the obvious thing to do is to get rid of the tension. So let's multiply both sides by 8. And then we can subtract these equations with each other. So we have 7mg, the 8t's that cancel out, and then I have 8ma1 minus ma2. And then of course the mass, they cancel out, so minus a2. So now I'm ready to substitute this relationship into this equation. So I have 7g equal to 8a1. So a2 is equal to negative a1 over 8. So we have 2 negative signs. So this becomes plus a1 over 8. So this becomes 65 over 8 a1 7g. So you see that a1 is equal to 56 g divided by 65. So this is the answer. And then incidentally, of course, you can use this result to find a2 as well. So a2, all you have to do is just to divide this by 8 and then give it a negative sign. So you see that this is equal to negative 7 over 65 g. So this is the answer.